And I want to thank all of you. Please take this information today and share it with your neighbors and friends. And we are recording it, and we hope to have that up on the Joshua Basin Water District website or other places. We'll let you know. So with that, I'm going to pass this over to Laurel Rogers, who's on the team from USGS that drove out here. Laurel, thank you.
Well, thank you for coming out today. This is great. I think you'll enjoy the presentation today. We're going to start with Dr. Tracy Nishikawa. He's going to talk a little bit about groundwater in general, aquifer systems, give you a little groundwater 101. He is been with the survey for about 23 years. He got his PhD at UCLA in civil engineering. And after Dr. Nishikawa, Dave O'Leary will be speaking a little bit more about the specifics of your aquifer systems and basins, and you'll enjoy this talk. So thanks a lot.
Well, thanks for everybody for coming out. And again, thanks to Joshua Basin Water District for hosting this and the other water districts for co-sponsoring it. Just a public service announcement. If you're expecting a Coachella act today, you're in the wrong place. Go out, turn right, turn left. I'm not looking at it. That's a little dark. All right. Next slide, Laura. All right, so here's just a brief biography for Dave and myself. Again, I've been with the survey for 20 some odd years. Dave's just a young pup, and it kind of gives us an idea of what our areas of expertise are. Next slide. So here's an outline of today's presentation. I'll be giving USGS 101, just like who we are, what we do. I'll give a groundwater 101 talk, just so everyone gets on the same page. Then Dave will give a talk on our research drilling techniques specific to the unsaturated zone. I believe he'll also touch on the saturated zone. And I'll be talking about the unsaturated and saturated zone too. And then we'll both be giving an overview of USGS activities in the Morongo groundwater basin, which includes the Warren Subbasin, Yucca Valley, the Joshua Tree and Copper Mountain subbasins, where we are right now, and the 29 Palms Marine Corps base. And then we'll wrap things up with some questions and answers. All right, so the USGS is part of the Department of Interior. We're an agency within the Department of Interior, which is an executive branch of the government. And the thing about the USGS is that we're a non-regulatory agency. That is, we don't make any rules. I think we break plenty of rules sometimes, but we don't make any rules. And for example, like the EPA. EPA makes rules, can only pollute so much and stuff like that. We collect data. We're known for our unbiased scientific data. Next slide. So the USGS was established in 1879, and basically it was an offshoot of the western expansion of the United States. They wanted to map the minerals. They wanted to map the rangelands, the land, open lands, etc. And so one of the people that helped establish the USGS was John Wesley Powell, the guy who floated down, one of the first people to float down the Colorado River. He was also one of the first ones to understand the importance of water in the arid Southwest, and which carries forth, as you know, today. Next slide. So again, the USGS is a science bureau of the Department of Interior. We are combined earth, biologic, and physical sciences together. Again, we were established in 1879. And today we conduct scientific surveys, investigations, and do some basic research. Next slide. So our mission is to serve the nation by providing reliable scientific information to describe and understand the earth, to minimize loss of life and property, manage water, biological energy, and mineral resources, and to enhance and protect our quality of life. So, as I said earlier, we're a scientific organization. We don't make any rules. We're non-regulatory. We don't manage any natural resources or land management like the Bureau of Reclamation or Bureau of Land Management. We also support other DOI bureaus like the Bureau of Reclamation and Land Management with scientific information. And we also work in partnership with many, I don't know if it's 2,000 agencies, but I don't know where that number came from, but state, local, tribal governments, the Joshua Basin Water District, High Desert Water District, the Marine Corps. All right, so the USGS was, I don't know, a couple years ago, was reorganized into 7 what they call mission areas. That's to recognize the multidisciplinary nature of science, of the earth sciences, natural sciences. All right, what we're going to worry about is the important one, and that one's the water mission area. So water talks about groundwater. We have what's called the National Water Quality Assessment Program, which is ideas to take a snapshot of the nation's water quality and then say, okay, it's good, it's bad, whatever. We do basic hydrologic research in terms of scientific techniques, analytical techniques, numerical techniques. We operate a stream gauge network, which is important for flash floods, flood forecasts, etc. And we have what's called the Cooperative Water Program. Now, the Cooperative Water Program is what Dave and I do most of our work with. That's where we work in partnership with those state and local governments. And it's kind of it's a cost-sharing partnership between the federal and local agencies. Well, got cut off at the bottom. This is just our website for the California Water Science Center. Each state has a water science center, except for those little states back east that, Delaware and Maryland and stuff like that. They kind of glom a couple of those together. But California is a big one, so we get our own water science center. Usually the headquarters is located in the state capital, so our headquarters are in Sacramento. And Dave and I and Laurel are out of San Diego, so we're kind of like a branch office. So this kind of gives you an idea of kind of things what we do. We look at changes in stream communities after a fire or logging. We're looking at climate change. We've done work, say, looking at nitrate pollution from dairies. I don't know what this one last one should be, but we'll just keep on going. Next slide. We also develop what's called the groundwater models. I'll talk about that more later. This kind of gives you an idea of where we've developed models. We recently completed a model here up here in the Santa Rosa area. We've completed models of this area, of Yucca Valley, Warren Subbasin, and of Joshua Tree, for example. Okay, stream networks again. We have stream gauges, over 1,500 in California. And so that's it. Besides us being very heroic, you don't have to ask us how heroic we are because we were very, we don't like to brag or anything. Are there any questions about the USGS in general? All right, great. How do I switch to another one here then? Yeah. Lecture. Yes. All right. So LEC. All right, now a few technical questions, problems. There you go. There you go. Oh. All right, here you go. So now we're on to groundwater 101. All right, so groundwater is part of the hydrologic cycle. Okay, so water evaporates from the oceans, it goes in the clouds, it comes across the mountains, falls as rain or as snow. Some of it will run off into streams. Some of it goes into the groundwater system, and then it comes back into the ocean. I mean, that's simplistically the hydrologic cycle. Now, no. All right, so she's a little quick on the trigger there. So fresh water, based on this, look at this pie chart. Okay, most of the water on the planet is in the oceans. Only 3% is fresh water. Of that 3%, 30% is groundwater. So roughly 1% of the world's freshwater sources in the groundwater system. Oh, and before I go on, I forgot to acknowledge these slides were provided. The bulk of these slides were provided by Kathy Thorby-Arneson, who is a geology professor at San Diego State University. She kindly loaned these to me. Next slide. So as I said, okay, groundwater is part of the hydrologic cycle. You have rainfall falling on the land. Some of it runs off into creeks, streams. Some of it is evapotranspirated, it's evaporated or it's transpired by plants, and some of it infiltrates into the groundwater system, into the ground surface. Next slide. All right, so many people visualize underground rivers. Groundwater is in underground rivers. Well, next slide. So that only happens very rarely in what's called a karst or a limestone aquifer. So here's a karst aquifer here in Kentucky. The green stuff is a fluorescent dye. There's the well right there. All right. So that's only in very rare situations that you're going to have an underground river like this. Most times, next slide, groundwater is held in small pore spaces within rock and soils, shown in this figure here. So, you know, here you have your soil particles here, and you have the groundwater between in the pore spaces. All right. Next slide. So groundwater accumulates over an impervious or an impermeable material. And we got to realize that it flows very slowly. It flows on the order of maybe, again, a few meters per day. So we're talking 3 feet a day, something like that. We're not talking about it moving right along at 20 miles an hour or something. So if you look at the cartoons at the bottom, you have the sand-filled dish, okay, and it's got an impermeable bottom. Pretend this is a stream right here. You've got recharge coming in. It accumulates at the top, and in fact, the groundwater that's within the soil connects to the stream right here. Next slide. All right, so the basic idea of this slide is that groundwater flows downhill like every other kind of water. Water flows downhill. That's just the basic idea of this slide. Next slide. All right, so here's a couple of important terms that you hear when dealing with groundwater. Porosity and permeability. All right, so porosity is a parameter which describes the amount of open space in geologic material. It's defined as the volume of the voids, that is that open space in the pores, divided by the total volume. So usually porosity ranges from 0 to 50%. So these open pores can be filled with water or air or both, all right? And it's got cut off at the bottom, but if you have soil, air, and water, that's called the unsaturated zone, okay? So that means you have a mixture of air and water within the pore spaces. If you go and if all the pore spaces are filled with water, then it's called a saturated zone. All right, so, I didn't know I had a little, wow. That's pretty nice. Okay, I did that. Yeah, right. So rocks can have a high porosity, but if those pore spaces aren't connected to each other, then the water can't flow. Okay, so and then on the other side of it, to follow up on that idea, you have the idea of a permeability, which describes the ability of that water to flow through the geologic material. So you can have a high permeability material, or you can have a high porosity material with a low permeability, like clay. Clay has a high porosity, but it has low permeability. Well, what? Ah. All right. So one definition of aquifer is a geologic material that can transmit large quantities of water and that are highly permeable. There's also been, I've seen definitions of aquifers that you can extract water economically, whatever that means. One person's economics is another person's I can't afford it. But I mean, you know, if you decide that it's important and you're willing to pay for it, obviously that's one thing too. So examples of geologic materials which are typically aquifers are sand and gravel alluvium. That's what you find around here. Sandstone, not so much around here. And we've already seen pictures of limestone and karst aquifers. Here's just an idea of a high permeability material would be gravel and sand. Your silts, clays, and shales are your lower permeability material. Next slide. So geologic material that cannot transmit significant amounts of water. The word impermeable may be overstating things, but water doesn't flow so well through it, are called aquitards. Okay. So then typical aquitards are clay and silt alluvium. For example, that's what we run into, say, out in Antelope Valley. There's an aquitard that's a thick clay layer that minimizes flow, vertical flow through the system. Shale and siltstone. The last concept that's similar to permeability is the concept of hydraulic conductivity. Hydraulic conductivity is a function of the soil and the water, and it's kind of what we call a lump parameter. But it basically still defines or explains how water flows through a groundwater system, how easily it flows. So the higher hydraulic conductivity, the easier the water flows through the groundwater system. So you can see here, and this table just shows, say, clay, which we already talked about, has a high porosity, but has a really low hydraulic conductivity. I mean, this is meters per day, but it's close enough. You get the idea. Here, with the gravel, you have a 25% porosity, but then you're talking about 205 meters a day, 70 feet per day. That's a pretty good hydraulic conductivity. And you might see that term bandied about sometimes when you're reading a groundwater report or something like that. Next slide. All right, so as I talked about before, we talked about the unsaturated zone. That's between land surface and what we would call the saturated zone, or the water table. So say here in Joshua Tree, what are we, like 300 feet?
Here it's about over 400.
400 feet unsaturated zone. That's a pretty big, thick unsaturated zone. Back east, I was just talking to somebody, and back east you might have a 3-foot unsaturated zone. Okay, so it's completely different here. Okay, then there's the capillary fringe, and that's kind of the gray area between the unsaturated zone and the saturated zone. Okay, it's getting more saturated, but it's not, there's still some air in the system. Okay, and then you're down into the water table. That's the interface between the unsaturated and saturated zone and unconfined aquifers. All right. Okay, yeah, we'll be talking about unconfined aquifers in a little bit later. And then, of course, the saturated zone, we already talked about. That's where the pore space is filled with water. There's no air in the pore spaces. All right, here's another definition of aquifer. Okay, but then, right here, that's sufficiently permeable so as to supply water to wells. Okay, and then we already talked about the aquitard here. Okay, so here we have an unconfined aquifer. Okay, it's an unconfined aquifer because it's open here to atmospheric pressure. Okay, here you have the aquitard, and under certain circumstances I'll talk about later, it'll be under pressure. The water will get pressurized. Okay, so unconfined aquifer, again, it's under atmospheric pressure. Okay, so the top of the saturated zone is known as the water table. also known as the phreatic surface. All right, one thing that we've got to remember here is that these ideas of water table and, well, basically the water table. All right, so, okay, you strip away all this dirt, you get down to the water table, and what are you going to see? You're going to see, actually, you're going to see dirt or granules and water. Granules and water, granules and water. As you zoom back out, then it'll look more like a lake. Okay, that's really an idea of a water table. You're connecting the dots to make the idea of a surface, but there really isn't a surface because you got this dirt in the way of the various pieces of the water table. So I don't know if that makes sense, but it's just it's a theoretical construct, so it makes it easier for all of us to understand, especially me and Dave. So, and then you can see anyway. So that's the idea of an unconfined aquifer. Next slide. Okay, so now we're talking about confined aquifers. So here we have a confining layer or an aquitard. Okay, so water can't flow through it or not flow through it very easily. All right, you have recharge coming up in here, and this recharge pressure, because no water can flow through this aquitard or confining layer, it pressurizes the system. So if you struck a straw, or better yet, a well through into the confined system, and say the wellhead was below, let's take a step back. So then again, here's an idea of the piezometric or potentiometric surface here. Okay, again, that's just a theoretical idea to help us better understand. So if we punched holes in this confined aquifer system, okay, figured out where the water levels were in every well, and then drew a surface through it, that would be the piezometric surface or potentiometric surface. So if the potentiometric surface is above land surface here, and we would suck a well in here, this well would flow, and then would be called the artesian well. All right, you might, okay, remember Olympia beer? They had the artesians? Yeah, so that's the idea. You had the artesian well, right? I remember I had a I brake for artesian bumper sticker on my car back in the day. So then here you have another well that's in the confined system, but you know the wellhead's above the potentiometric surface, so it's not flowing, but still a confined system. And in here, locally, it's unconfined. You have unconfined aquifers.
Is that because there's not enough pressure? Is that why?
There's no confining layer here. Next slide. Okay, so we're getting down to the end here. So the idea I want to talk about next are groundwater basins and subbasins. So a groundwater basin is an alluvial aquifer or a series of stacked aquifers with reasonably defined lateral boundaries and having a defined bottom. So although it got cut off at the bottom here, this is the Morongo groundwater basin as defined by the state. Okay, and so usually this is probably some kind of bedrock here that is defining the boundaries here. But sometimes it could be a political boundary. Then here within the Morongo groundwater basin are a number of subbasins. So this is a subdivision of the groundwater basin created by dividing the basin using geologic, hydrologic, or institutional reasons. So for example, again, hopefully we'll see it better on some other slides. A lot of these subbasins are defined by faulting. Okay, there's a lot of faults around here. And so what we found is a lot of times faults will control groundwater flow. All right, so then, so these subbasins are defined a lot of times based on faulting. So let's now talk about groundwater wells. It's a hole bored or drilled or dug into the saturated zone. Okay, like the wells that we've installed, say in Yucca Valley, we use those to measure water levels in aquifers. We can obtain samples of the water for water quality analyses. And, you know, if it's a production well, you can use it to pump water out for water supply. So there's a couple parts to a well. There's a well casing where there's no connection with the groundwater. There's the well screen, which are open slots that allow water to enter the well. And so depending on what you want to do, I mean, let's say you want to do monitoring or sampling, you may set these wells, and Dave will talk about this more later, at particular depths beneath land surface so you can collect water levels or water quality samples at specific locations beneath the surface. Next slide. So then these are just some cartoons of how it might be difficult to place a well. You know, I mean, here you might have it in a sand. This might be in a clay. Again, this is supposed to be a fractured system here. This well happened to hit a fracture where this well missed a fracture. In this cartoon, this well hits what's called a perched layer. That is, there's a clay layer that some water bounded up on, and it was just managed to hit it, where this well did not. Now here's an idea that we all need to be aware of, is the idea of drawdown. So when you pump water out of a well, the water level in that well will decline. That's called drawdown. All right. So, and the results, so here's your drawdown here. So this is your initial water level, and then you start pumping. So here's your drawdown here, X number of feet. All right, so that, and then it's not just, you know, a cylinder, it's actually kind of a cone here, also known as the cone of depression. So you can see that, let's say you had another well right over here, then that cone of depression could be affecting that other well. And then if you start pumping out of that well, then you have double the drawdown that you would have out of one well. Next slide. So, so let's talk about recharge and discharge areas. So basically, I mean, what you have here is you have rainfall falling, let's say on this mountain here. Some of it runs off, some of it evapotranspirates, some of it hits the water table, and it'll flow downhill, right? And enter, say, it'll be discharged into a stream. But the important part is that you have these recharge areas that will recharge the groundwater system even at a lower elevation. So discharge, so again, surface areas where water flows from surface into the groundwater are called recharge areas. So most of the recharge around here happens, say, in the Little San Bernardino Mountains. I don't know which way am I? Yeah, I think it's that way. Okay, so then we have discharge areas where water flows from the groundwater into the ground surface. And so that might be, say, a stream like here. So a lot of times in maybe alpine areas, other places, groundwater is an important part of stream flow. It supplies what's called base flow, the minimum amount of water, even when you're under a dry condition. Groundwater will supply that stream flow. So here you got your recharge area. Here you got your discharge area. And the idea behind this one is that these are flow paths. That's the path that a groundwater or water molecule might follow from the recharge area to the discharge area. And the idea is that it could be on the order of days to thousands of years. Okay, I've just finished a project up in Santa Rosa. Some of the flow paths were on the order of 30,000 years. To 30,000 years to go from the recharge area to the discharge area. Okay, so yeah. So last couple things are groundwater springs. That's where groundwater flows freely from the ground surface. See, there are springs around here, as I understand it. So that's where the water table intersects the ground surface. Now here we have a simplistic, what's called a perched water table. An aquaclude is kind of like an aquitard, but a little bit more permeable. We're not going to worry about that. But here we have the perched system intersecting land surface, and you have the spring. Now that usually doesn't happen so much around here. Oh, next slide. Sorry, Laurel. All right, so down here we have a fault. We have the water table down here. We have a fault here. And then we have the more permeable material up here. And so you have the water table hitting this fault and seeping out along this fault face right along in here. And that happens a lot around here. All right. So groundwater models. Okay, we're going to be touching on that a bit in this talk today. So groundwater models today are computer models of groundwater flow used to simulate and predict aquifer conditions. Okay, back in the day, before they really had computers, they actually built sandboxes. And after that, they actually built electrical analogs, big rooms with not transistors, resistors and capacitors and things that were used to mimic groundwater flow. So groundwater flow is defined or described by mathematical equations. So these mathematical equations are solved by these computer models. And usually they require some simplifying assumptions. Now, for example, here's a figure of the model that we developed for Yucca Valley or Warren Subbasin. Okay, so some of the simplifying assumptions is that, again, okay, we already talked about the water table. It's like a sheet of water. You can see it in your mind, right? It's like your swimming pool full of dirt, and you can still see the water, right? So that is what's called a continuous surface. Right? You can get a water table of measurement at infinite number of points anywhere in your swimming pool. Okay, that would be really hard to solve. So you have to say, okay, I'm going to look and try to solve it at particular discrete locations. And so that means what's called discretization. Now all those little squares there are where we would solve the model, say at the water level, in the model. Okay. Then obviously time. Time is continuous, right? You get milliseconds, nanomilliseconds, whatever it is. So you have to discretize time also. Next slide. So this is just what a model is. It's a simplification of the real hydrologic system, hydrogeologic system. Okay, it's a supplemental tool for water management. So you can test what-if scenarios with the model. Okay, again, it's a computer program. Okay, it's you can approximate how the water, if given the situation, talks between surface and groundwater. And it's a tool to estimate your water budget. That is, how much water is flowing in, how much water is flowing out, how's your bank account, your water bank account doing. Okay, a model is not a unique solution because of these various simplifying assumptions that you had to make. It's not the true and absolute answer. Well, maybe my models are, but no. No, it's not the true and absolute answer. And it's not certain in the simulated and predicted, so there are uncertainties. I mean, there's errors in the data that you put into it. There's an old saying in computer programming, garbage in, garbage out. So if you have some data that aren't so high quality, that can affect the results, right? And also, obviously, it does not replace field investigations and the need for real data. All right, so that's it for Groundwater 101 in a nutshell. Are there any questions? Yes.
And let's say the water table is 500 feet and you have a year of heavy rainfall. How long does it take for that to percolate down and build up a water table?
Around here? Well, it could take a long time, actually. Recharge, we've done some work here. A colleague of ours has done some work in desert basins, and natural recharge could take hundreds of years to reach the water table.
Hundreds of years.
Hundreds of years.
The other thing to realize too is that rainfall, in this type of environment, the desert plants are very good. They're very efficient at utilizing whatever water hits the ground. And so if we have a rainstorm here and it's not a 1,000 or 100-year event, it's just a good rainstorm, and it falls on naturally vegetated area, very little of that water will make it below the root zone, say 8-10 feet down, because those plants have evolved to use every drop of water available. So most of the recharge will come through where that water can overwhelm the system, which would be maybe on the mountain fronts where it's running across bedrock, or in the stream. So say like Quail Wash, where you have this huge volume of water coming down the wash and it can overwhelm the plants and actually get in and recharge. So that's something to think about, is that every time it rains, especially out here on the basin floor, that natural vegetation is very efficient at using whatever precipitation falls.
The other question on the drawdown, if this platform here is the aquifer, and I've got a pump sitting down into that aquifer, I don't understand the drawdown theory you guys threw up there because this is sandy soil, it's water, sandy soil. I got a pump and I'm drawing. Yes, I'm drawing right near my filter, because my pump's buried down in there, but I would expect that drawdown to always come back up to some level, depending on how it can black flow. But, so when you say, I put a well here, and I got it down, now I forgot what it's.
Cone depression.
Cone depression, yeah. So, okay, what?
You're calling it a down draw, right?
Cone
I've got multiple wells within, say, 20, 30 feet. I could understand a bigger drawdown, but eventually that aquifer is going to fill back up to some level across the whole aquifer.
Well, okay, so I'm assuming that you mean it's going to recover after you stop pumping.
Yes, well, to a certain level, obviously,
Yeah.
it's going to keep going down.
All right, let's say that your natural recharge is 10 and you're pumping at 20, so you're going to not recover. So no,
That's where I'm getting confused, sir.
but hang on for a minute. So then, now let's assume that you're pumping for a day and you turn it off. Yeah, you're gonna have recovery. I agree. But am I saying that it's going to? You know, there's a lot of things that it depends on. It depends on the geologic material. It depends on how much recharge you have. I mean, that's just that cartoon was so you can have so you can actually know the term drawdown. And I mean, there is drawdown. You pump a well, there's drawdown. Okay, you know, if you pump a well, you're going to have a cone of depression. Now, size of cone of depression, the amount of drawdown you have is going to be a function of your aquifer material.
And the rate of pumping. And it also, that I think maybe what you were getting at too, that cone of depression will stabilize. So you have, say like you pump at 100 gallons per minute for a day, you're going to draw, whatever, the well may draw down 5 feet within the first hour, and then it just sits at 5 feet. So you can stop that. And what that is a function of is that the well is drawing water in from 360 degrees on this. If the well was in the middle of the stage, it's pulling water from the entire stage. So you have this radius, this zone that the water's being drawn from, and eventually the radius gets big enough that it's contributing enough water that drawdown then stabilizes, and that's what's called steady state conditions in the pumping. And that the cone of depression exists, but it's stopped. It's not a dynamic cone of depression. It's locked into place.
Is that the effective radius? Yeah, so then that radius is called the effective radius, where it doesn't draw down anymore. I mean, it's not going to, yeah, you're going to have it's going to be a finite distance from the well. Right. Dave?
What is the percentage of reliability with your models?
That's a, well, are you talking about my models?
You're asking,
Oh,
you're asking the wrong guy.
Again, you know, it's a function of the data that are used to build the model. And then, you know, again, this project we just finished up in Northern California, we had to estimate a lot of the pumping. I mean, that's a big part of the stresses within the system. So that's a good source of error.
Because it's not metered.
It wasn't meters. We had to estimate it. So, you know, it's kind of hard to say. It's a model by model problem specific. I mean, the models themselves are very good. I mean, the models that the USGS has developed, ModFlow is one of them. It's a industry standard worldwide. But you know, it just depends on on the application, on the given application. I guess that's what I should say.
So that's about 50%.
Oh, well, mine is, you know, a lot better than that. All right.
Tracy, are you going to talk about, are you talking a little bit more about models, Dave, later? Or?
Yeah, we're going to touch on our models here in this local area.
Why don't we do two more hands? We'll do two more questions.
So with the recharge basins, how you said it could take hundreds of years for it to come down through any area, but then we have these recharge basins, I guess, where the idea is like in Palm Springs, you pump in a ton of water and maybe in the lowest area of the basin, and that's supposed to flow out so that all the wells are able to pull from that
First down, then out.
recharge, right?
Yeah.
And so how long does that take for it to reach out and to be able to replenish that?
Depends on
Well, around here it's going to be months.
it's fast.
Okay, okay. There's a difference between what that gentleman asked and what you're asking. Okay, what he was asking was like a one-time deal. Okay, If it rains, it soaks in, how long does it take? Out here, you're going to have, you're engineering some basins, and you're going to continually put water in. And as the soil wets up, it'll flow through faster. Okay, so first it's going to take, I don't know, maybe a couple months for it to get down to the groundwater system out here. But then once that soil column wets up, it'll move down really fast. But, you know, out in the desert where it rains, and under natural conditions where it doesn't rain that often, right, and the soil gets really dry, you have to wet that thing up first, then it'll start recharging. And then, you know, I want to take a step back on that 100-year flood question. Now remember, if you start having a flash flood, the water's not hanging around too long to soak in, right? It's moving down to Coyote Lake or someplace. So you have to have a reasonable rainfall rate for it to infiltrate. What was the last question?
Over there.
I don't know.
The cone of depression, the thought that was going through my mind is even when you do like a bathtub and you let the water out, it has that swirling effect and the water can't fill in fast enough where it ends there. And that's with 100% saturation, just water and no material to move through. So it would make sense what you're saying. The water goes out, and for a certain period, it's going to make that cone, right?
Mm-hmm.
Is that when you
Steady state, yeah.
Yeah, but the bathtub, I mean, you're going to have, assuming that you're not filling it up simultaneously, right? You have the water levels going down, so it's a little bit different question, but this is, I guess it's analogous. All right, one more question.
Let's see.
Okay, you guys duke it out. That might be the Coachella show, by the way. Okay.
You have several wells, let's say 200 feet deep, and they're producing, not here necessarily. And then someone comes along with, let's say, 800 foot deep, 1,000 foot deep well, but goes through an impermeable layer. By piercing that layer, can the other wells go dry? Now, the water on top of that impermeable layer is going to like break through the hole that people dug, or is that not really working?
Depends.
Well, assuming that they built the well correctly and they actually sealed it correctly, I don't think, and it's an aquitard, that there should be very little vertical communication between the shallow wells and the deep well.
That said, you can, so that's a good point. You can get these, you have basins that are divided up by aquitards, and maybe you have good quality water shallow and poor water quality deep. And you'll see this in places like the Central Valley. They'll put in these long screen production wells through aquitards, and all of a sudden when these wells are idled, they become conduits for water to move. Water will move from a source of high pressure to low pressure, so these wells can become conduits for water that wouldn't under natural conditions. These aquifers were separated from each other. Those wells can then become conduits, and if you punch enough wells in, you can move one water quality to the other. You'll also equalize the water pressure.
All right, we better move along here.
And we'll do more questions at the end. So if they're hard questions, forget them and throw us the softballs. So Tracy talked about concepts of groundwater. So we have all these terms. I'm going to talk a little bit right now about the nuts and bolts, and especially as it applies to here in, say, a desert environment, is how are we going to collect some of this data? How are we going to look at this data? We can use that data to then, the better data we have, the better groundwater model we can build, the better predictions we can make for the system. So I'm going to talk about something what we call unsaturated zone monitoring sites, and I'll explain more what that means. So I'll briefly talk about these boreholes or these monitoring sites. I'll talk about the rationale and where we've constructed some of these throughout the Mojave Desert, how we drill them, the design and construction of them, how they're instrumented, how we get data, and then the results, what we do with that data. So where do we do this? We talked about unsaturated zone and saturated zone. So here we have our water table here where you can see some wells here. We have this unsaturated zone. So typically we're going to put these unsaturated zone monitoring sites not somewhere back east where it's 3 feet to water, but maybe somewhere out here where we're talking 100, 200, 300, 400, 600 feet to water, where you have this deep zone where there's a lot of space. It takes time for water to move down. You can get a lot of things happening physically, geochemically, as the water makes its way down. So these are the zones where we're going to put them. Another name for the unsaturated zone is vadose zone. So if I throw that term around, that's what I'm talking about, this unsaturated zone. Next slide. So what's the concept? These unsaturated zone sites, we're looking at the movement of water from the land surface down to the water table. So kind of a simplified model. This would be an artificial recharge, but this could also maybe be a wash where the rainwater's filled the wash, and we're looking at water moving from the land surface, next slide, down. And this would be our unsaturated zone site. This is a really simplified model. So we have this hole in the ground that we're trying to understand the movement of the water between the land surface and the top of the water table as it goes down. So these sites, USGS, we didn't really invent any of the technology that goes into these, but it's a unique combination of technologies, and we've installed these sites here primarily throughout the Mojave Desert. So here we have down Joshua Tree, Yucca Valley, several sites up in the Victorville, El Mirage, and then out in Antelope Valley, and then down here off the 10. So we have numerous of these sites. They've evolved and developed through the years as really effective tools for monitoring recharge. So why do we do them, and how do we do them? Typically we'll build them, as Tracy mentioned, in cooperation with local water agencies. The water agencies interested in what's going on in movement of water from the land surface to the water table. And they're designed to measure the quantity, quality, and movement of both artificial and natural recharge from the land surface to the water table. So that's why we're installing these sites. So first of all, how do we drill them? They're drilled using what's called ODEX. I think the acronym is actually Swedish, or the technology is overburden drilling and exploration technique. And instead of using water or mud as a drilling fluid, it uses air. And the reason is we're trying to unstudy this unsaturated zone, this dry zone above the water table. If you drill it using typical drilling methods, which is to use mud or water to move the cutting materials, you're actually saturating your unsaturated zone, and then you're not able to study it because it's wet. So you'd say, oh wow, the water's all the way to the land surface. So we use this ODEX drilling technology, which uses air to move the cuttings as opposed to water or mud. It allows us to make what we call high quality cuttings. So these are actually 1-foot piles of cuttings. So you can imagine, we usually lay them out in 10-foot intervals, and what's neat about this is you'd say, okay, this is at 1 foot, 2 foot, 3 foot, and you can walk your way down 500 feet of material. This is laying out on the ground. And so what this allows you to do is, with a high degree of precision, try to understand what's going on. And one of the important things with this is that the movement of water through the unsaturated zone, the rate at which it moves, it's only the limiting factor are your fine-grained units. So if there's clays or silts, that's what's going to slow it down. And even a 6-inch or 8-inch foot thick layer of clay could dominate this 500-foot system. So you know that little tiny zone is going to determine how fast the water makes it down. And this allows us to hopefully catch those zones and see them. So you can see these redder soils are probably old soil horizons. You could look at some better material for the water to recharge through, that kind of thing. This drilling technique also allows us to collect cores at selected intervals. The core, so that when you drill, you're disturbing the material. The drill bit's chewing it up, it comes up. You can tell something geologically about what the material is, but it's not an in situ sample. The cores are actually, send down a core barrel and you're collecting material intact. Bring this up. And then we can do a whole lot of tests on these back in the lab to determine the properties of the native materials. So we can determine, we'll get what's called saturated hydraulic conductivity, where you put these in columns and push water through them, and you can learn how long it takes water to go through this 6 inches of material. That data can then be used to feed into the models, better data in terms of how long it would take the water to move down. So sampling techniques, this is what you do at the USGS when you're low on the totem pole, is sit there with your dust mask in 104-degree heat and fill buckets with dirt and wonder why you ever went to college. So this is sampling. Again, we're sampling at 1-foot intervals. You can see laying them out. But again, this allows us through time to really leisurely, not leisurely, but to look at them with a high degree of precision, what's going on with the material. It also allows for relatively large amounts of material to be collected, so then we can then take that, run what are called batch tests or column experiments if we're interested in how this material may interact with recharge water. So there's a lot of benchtop lab tests you can do with that. Next slide. I mentioned looking at the finely discretized lithology. So we'll take subsets of cuttings and we'll archive them in boxes, and you know we have shelves of these from the boreholes because you never know when you're done. It's relatively expensive to drill these holes, we try to keep this data for all time, so because you're never done looking at it. You think you understand it, and maybe 10 years later you'll come back and say, oh, what was going on at 100 feet? Why is this occurring here? And we have this material archived in our office. I mentioned that thin units can really dominate the movement of recharge, and as I said, you get ample material for laboratory experiments. As we're drilling with this technique, we do what's called real-time analysis, and I'm going to simplify this a little bit, but what we do is we take a little bit of material. We actually use like a 35mm film canister, collect that material while we're in the field, sieve it, and then we mix that water with an equal volume of DI water. DI water, it's deionized water. It does not transmit electrical current like normal water would, so we have what's called an EC meter, electrical conductivity meter. If you were to stick this EC meter in DI water, you would get a reading of 0. That water does not conduct electricity. When we dissolve the material in with some of that cutting material, you're dissolving any soluble salts out of the material. And so those soluble salts will then translate into an electrical conductivity. This is a vertical profile of each foot of electrical conductivity. So what it is an analog for soluble salts in the material. And what those soluble salts indicate possibly is previous water movement. So back under different climatic conditions, maybe there was a clay layer, things were wetter, water was perching on this layer. Now when we drill it, we don't see it, but you can see it in this, that okay, what was going on here? Why are these soluble salts here? Is this somewhere during our recharge that the water may hang up? That's not evident. So that's one thing you can do with these. Then we're going to instrument the holes. So the holes, like I said, are designed to measure the quantity and quality and the movement of artificial and natural recharge. So one of those methods is we're installing these devices to try to track the movement of the water from the land surface to the water table. And I won't go into this too much. We have several types of, they're basically electrical instruments that measure how wet or dry the soil material is. Dielectric permittivity sensors, heat dissipation probes, advanced tensiometers, and then temperature sensors. Probably everyone knows what a temperature sensor does. The rest of these, again, are designed to measure how wet or dry. What's called a suction cup lysimeter allows us to collect physical water samples from the unsaturated zone. So if you want to collect a water saturated zone sample, you put in a well, pump the well, you get a water sample. But if you were to put a well in the unsaturated zone, it's never going to make water. These suction cup, Tracy pointed out that even in the unsaturated zone, there is soil moisture bound up in the pore spaces. These suction cup lysimeters allow us to collect that water. So you're able to not only monitor the physical movement, but then look at the chemistry of that unsaturated zone water with these instruments. And then what the lysimeters also allow you to do is once the wetting, say it's at a recharge site, once the wetting front starts moving down, you can monitor, as opposed to just getting a water quality sample, say in the recharge pond, and then in the well at the water table 6 months later, you have a series of these suction cup lysimeters. It allows you to monitor the geochemical changes that may be occurring in the water as it's moving from the land surface to the water table. And those changes may be beneficial, they may be something that you don't want. You can get both. So I won't go too into this other than to say, again, these instruments, these are the advanced tensiometers, heat dissipation probes, and these dielectric permittivity sensors are to measure the wetness or dryness of the material. And the suction cup lysimeters are used to sample the material. And I should mention, these sites, well, we'll talk about these later, but these are existing, these unsaturated zone sites. There's, I think, 3 or 4 down in Yucca Valley. There's 4 sites here in Joshua Tree, and I showed them throughout the desert. So they're around town. They're being used to monitor artificial and natural recharge. So this shows a completed site. There's a lot going on here. The real thing, and it's a little hard to see, this is the construction of the borehole. So this is the water table down here. This site, it's hard to see, but this is about 380 feet to water right here. This would be the land surface up here. You can't see all of these, but each of these is an instrument. So each of these is going to allow us, as that water makes its way from the land surface down, we're able to track the movement of the water all the way down as it makes its way to the water table. You can see a geologic section. So this is as the geologic material. This is based on those cuttings that we pulled out of the ground. You're able to construct a geologic column. These are some geophysical logs, geophysical data that we get from the borehole that tell us a little bit more about what material's there. This is a series of instruments. So these are what are called heat dissipation probes. I won't talk too much about them other than they're going to tell us if the material is wet or dry. Simplified version. So I want you to think of this axis here as what's called metric potential. It's a measurement, let's say, of how dry the material is. So the further up this y-axis you go, the drier the material. So each of these instruments is installed at a specific depth. So this pink one here is at 260, and this yellow one here is at 231. We'll just look at those two for now. This is time. We've got recharge water starting at the surface. This is sitting here saying, I'm dry, I'm dry, I'm dry, and then see it drop down. That it went wet. And what that allows you, this is how we interpret the data, is at this point in time, you would interpret that as that wetting front encountered that instrument at 231 feet. And so you can say, okay, the water took a month and a half to get from the land surface to 231 feet. And then you can see later in time, now we're at 260. This instrument's saying, I'm dry, I'm dry, I'm dry, I'm wet. And you're able to tell with a high degree of precision where that water is using these instruments. So this is just an example of some of the data that comes out of these and how it's interpreted. I'm not sure where we are. Did I talk too long? It went into sleep mode. Uh-oh. Your presentation is too boring, and that's on a Mac, so
That's still Microsoft.
the Microsoft is working. This is my cheat sheet, yeah. Slide 16 if you can find it.
16.
Yeah.
There we go.
So this is another type of instrument. So you can see there's what's called an advanced tensiometer here at 87 feet. We have an advanced tensiometer here at, this is 293 feet, advanced tensiometer way down here at 368. Again, this way to think of this, now this axis is flipped. We have a zero line. Anything above this line is considered wet or saturated. Anything below the line is dry. So let's look at this shallow instrument, 87 feet. It's saying, I'm dry, I'm dry, I'm dry. Here we have the wetting front arrive, and it goes wet. And actually at this site, they had multiple pulses of recharge. So they fill the pond, let it empty. Fill the pond, let it empty. And what you can see with this is you're actually seeing three distinct responses in this shallow instrument. Now the interesting thing here is as that recharge makes its way down, it's spreading out and your response is being dampened. So you look at this next instrument down, this 293 footer, you can see the peaks are kind of getting smeared out, and then you see it change over in the deepest instrument from wet to dry, but you don't see those distinct pulses of water. You lose that as it makes its way down. The response is dampened partially because it's so far from the source of water, the recharge pond at the surface. But again, this is the type of data that allows us to monitor those movement of water. So sequential geophysical logs, this is another way to monitor. We can collect geophysical logs, which are usually an analog, so you'll send down a tool down maybe a well, and it will collect typically electrical properties of the rocks that are out here. The rocks will conduct electricity differently depending if it's sand, clay. That's recorded by the tool, and you have an analog. You look at this squiggly line and say, oh, these are clays and these are sands. But if you come out and run this tool over and over again, you should always get the same log, because unless there's a big earthquake or something, these rocks aren't moving. So the electrical properties remain the same. However, hit the button once, Laurel. If you have water making its way down from the surface, you've wetted all this material up. Water typically increases the conductivity of a material. So the rocks haven't changed, but their conductive properties have. And so you can run what are called sequential geophysical logs over the well, and maybe the wetting front has made it to here. And what you should see is where there's a change between the two logs, you can interpret that as possibly a wetting front. And again, this is a way with anything in science, you want to come at it from a lot of directions, because it is the Earth is a complicated thing. It's complicated processes, and we're trying to understand it, and you're trying to approach this from multiple angles, and hopefully all these different methods are telling the same story, or at least pointing you in the right direction to understand the system. If you only come at it from one way, you may delude yourself into thinking that you understand it when in fact you don't. So it's important to have these other tools. So next slide. This shows a resistivity. So this is simply depth, and then we have a resistivity log, squiggly lines. So someone who really knows what they're talking about, look at this and say, okay, this is a gravel, this is a clay, who knows what this is? Click it once, Laurel. So we're going to look at this top one. This is a blow up of this section. Now we have a log that was run, it's hard to see there, but that was run in November, and the dark blue line. The next log, the blue line, the light blue line, was run in December. And see how down here they're the same because the water has not reached this depth here. But the light blue line is now less resistive. It's more conductive because it's wetter. And so what you could say with a high degree of precision is I would guess that on this date between the two logs, this is December 3rd, the wetting front's here. And go ahead and hit it again. So now you run another log. That one was, now we'll run on, that was December 3rd. We run on December 30th. Now we look deeper down. You can see they're right on top of each other. This is a little more subtle because of the material, but again, you can see where the wetting front is with a high degree of precision. Let's just go to the next slide, Laura. We do the same thing again down here. And this is all data collected from these unsaturated zone monitoring sites. So we're using that well as a tube to access the subsurface to collect this data. One more. This is data from suction cup lysimeters. Again, so everything else I've been talking about is to monitor movement, physical movement of water. These are looking at water quality. You can look at a lot of different things depending on what you collect it for, send it into the lab, analyze it. This is a really simplified version, but all this is specific conductance, so a measure of really the total dissolved solids in the water. And what we have here, this line here, is the water quality in the recharge pond. And this is a lysimeter, which shows a water sample from 20 feet, 59 feet, and 154 feet. And what you see is, through time, this is the specific conductance of the native soil moisture. And then as that recharge water comes down, the samples start to look like the pond water, meaning now we're actually sampling pond water at 20 feet. You can see later in time, now the 59-footer is starting to look more like pond water. And later in time, the 154-footer is starting to look more like this pond water quality. So again, these unsaturated zone monitoring sites monitor the physical movement, and now they also allow you to look at geochemical changes that may occur in the unsaturated zone. So this is kind of the whole story. This is actually from a site in Yucca Valley. We have depth below land surface. It's in this crazy unit called meters. I apologize for that. This is time since start of recharge. These are all the different instruments. And so what we do is we say, okay, we saw it in this dielectric permittivity sensor here. We saw it in a heat dissipation probe here. EM logs are the circles. We put all those together, and you see through time how long it took the water to get from the land surface down to the water table. In this instance, it's 135 days. Without an unsaturated zone monitoring site, you're blind. Water goes in. Where's our water? We don't know for 135 days until you can sample the well and see it. So it takes some of the black box out of the recharge process. The other way, so then this just shows that same recharge site, you have the water, the infiltration started after 135 days. You see this is kind of the water level, this is the water level in the well, and then we have this incline, increase in slope. So this is where the wetting front arrived at the water table. Now we're seeing a physical response at the water table. And then infiltration stops and things taper off again. So to sum up, the unsaturated zone monitoring sites, they aid in the evaluation of recharge in thick unsaturated zones, and this is both desirable, intentional recharge, or undesirable, maybe in the case of septage or something like that. They can aid in the placement of recharge sites, provide detailed evaluation of water chemistry during the migration of water. You can evaluate pulses of water as it makes its way down and how it's dampened at depth. And then they also provide quantitative data that can then be fed into the groundwater models. And that's it for unsaturated zone sites. I guess we do a couple questions about this if anyone has them. Or yes, sir.
I got one question about the whole thing. They keep talking about the point of the state running out of water. They're getting low on water. Damn ocean out there is filled. They got one desalinization plant, and it's not under operation yet. And they can put desalinization plants all along that coast, and we'd never run out of water. Why won't one of them get smart enough to think about this instead of making one plant to talk about the point we're low on water?
And I'm not an expert on desalinization, but I put them out in the South Pacific. It is an energy-intensive process, so there's a question that, I mean, and most things come down to economics, is do we have the money to pay for the power? And desal is not a silver bullet in the sense that desal creates large volumes of briny waters, and you have to do something with that water as well.
In the aqueducts where you got all that water that's gone out of it and let it sit there like the other places do. You got farmers that need water to be used on those farms.
Well, that brine water probably wouldn't be good for crops. But I think it comes down to economics. But I'm not a desal expert. I only know unsaturated zone hydrology.
I drank it out in South Pacific and I ain't dead yet.
Is this the one you're looking at?
What is the amount of water that it takes to start registering on your meters?
Depending, so I didn't go into that. There's that one slide, and I can talk about it maybe offline. Each of those instruments has varying degrees of sensitivity. So some of them can be, and I'd have to talk in terms of matrix potential, which is in cinibars, but it's you can measure, depending on the instrument, very small changes. And that's important for something like a natural recharge, where instead of this big flush of water, you have a more subtle event where it's not as big a volume. Yes, sir?
The issue of septic getting down into the groundwater. State's pushing people into that, like Becker Valley being towards
yes.
that type of system for that reason. But I hear we don't have much of a recharge out here anyway, so water doesn't get down there very quickly. You know, and there's just a question of, is it really necessary to go that when waste treatment plants use and waste so much water to begin with?
So when we say we don't have much recharge out here, there's not much natural recharge.
Exactly.
There is the anthropogenic recharge, so we're flushing toilets, putting it into septage. That is quite a bit more recharge. So that does indeed move further and deeper than the natural recharge does. It also comes down to a question of density. You know, as you get more pieces, so it's great if you have one house every 40 acres, the system can probably absorb that load of nitrate without you ever seeing it. But with growth comes the increased nitrate. The other issue is that the nitrate, so nitrate is NO3, it's very stable, it exists well in an oxic aquifer, it does not degrade. The goal is to get nitrogen to go to ammonia and nitrogen gas, is that right? But because the water is making it from the septage to the shallow aquifer, you're in an oxic zone, and so the nitrate will last for a long time.
So then the use of, you could call it an aquitard, I call it, I don't know if you ever biofiltration, where you just use a liner that doesn't allow it to go down, and you plant your plants in it and build it like a stream and clean it.
Yeah.
When it reaches the end, you can actually use the water.
Yeah, not that where you get it to go anoxic and hopefully have, denitrification.
So you're using a natural system
right.
to clean it, you're not going to get the nitrate problem.
And you see sewage treatment plants will even do that, where they'll have I don't know, their cattails or something like that out there, yeah, trying to treat it. So there are other solutions. But I think the two of those come down to a function of the density and the volume. And that's I don't want to touch that too much because it's the third rail and make it start getting tomatoes thrown at me up here, so. Yes, sir.
Declining rods, fact or fiction? What's the history of that?
I've done it with my father-in-law, and we found buried water lines in the yard. So on that regard, but the hydrologist in me does not believe in them at all. So I'm conflicted.
One more question.
I'm going to ride the fence on that one.
One more question. Yeah.
I just wanted to ask, we have some questions. Would you mind repeating the questions? Because, like,
apologies.
over there, I don't know what questions.
Okay, we'll start doing that.
It's up. All right, thanks, Dave. By the way, I always forget, you start talking and you forget things you're supposed to say, and you know how it goes. I believe there was like a groundwater 101 handout, maybe a 10-page. So that was provided or developed by the Sonoma County Water Agency up in Santa Rosa. It was kindly provided to us and to share with you folks. So please take a copy and everything, but I just want to make sure credit's given to where credit's due. Although I did find it, I did steal it, so I think I should get some credit for that. Okay, well, I saw the value of it, I should say. Let me put it that way.
I just want to let you know, there's plenty, so afterwards, don't worry, there's plenty. I ran off many.
Okay. Can it wait? Okay, so now we're going to just give a brief overview of the USGS activities here in the Morongo groundwater basin, specific to Warren subbasin, Joshua Tree and Copper Mountain subbasin, and the 29 Palms Marine Corps base. And I'll start off by talking about what's going on in, next slide, yeah, in, where am I on this thing? Okay, next thing I'll start off by talking about, no, too far. Here you go. All right, so we've seen this already, right? We've seen this figure already of the Morongo groundwater basin. Actually, now with that Warren and Joshua Tree cut off at the bottom. Again, there's many sub-basins within the Morongo groundwater basin. The USGS has worked primarily in the Warren, Joshua Tree, Copper Mountain, and the 29 Palms Marine Corps base. Now, we've worked, say, within the Warren Basin and Joshua Tree since the 70s. If you go, I believe there's a list of USGS publications. One of them is by Lewis, is published in '72. We've worked with the Marines out in 29 Palms since the 1950s. Next slide. So this figure is based on gravity data that were collected in the Joshua Tree and Warren subbasins. All right, so let's see here. We're kind of looking south to north. The little San Bernardinos are here. Here's, I think it's called Covington Wash. Basically, here's the Warren subbasin right in here. There's the Yucca Barrier there. This black line is just denotes or shows the lineament of the Pinto Mountain Fault. Over here you have the Joshua subbasin, and up here you have the Copper Mountain subbasin. Then out here you're going into the 29 Palm subbasin, and up here you have the Marine Corps base.
I'm looking at below ground.
Yes, that's like the basement material. That's the impermeable bottom that we talked about earlier. All right, so now we're looking east to or west to east. Here's the Yucca Barrier here. Here's the Copper Mountain here. Again, you can see it's a long, narrow basins. Next slide.
So there's going to be like alluvium above this, right? Just
Right, it's filled with dirt. Okay, we're standing on the fill right now. Okay. So actually, I was going to get to that, but I will get to it now. Go back. All right, so it's about as deep as 3,000 feet over here in Warren. There's two divots about 4,500 feet deep in Joshua Tree, and there's the divot in Copper Mountain's about 2,000 feet deep.
Copper Mountain, the upper left.
Right in here.
What are the sections that look like they've been scratched?
Like right here?
Yeah.
Okay, this is based on gravity. This is not like, we had a picture or anything like that. So this is a representation of the basement based on the gravity data were collected. And you can see basically it's a really steep face along here along where the fault was, or is. The Pinto Mountain Fault's right along in here. So it's really steep.
So the thing to do, when you go outside, you look at, say, the mountains and imagine them plunging down beneath the land surface we're standing on in places 3,000 or 4,500 feet down to the bedrock, and we're standing on that sediment that's filled that in.
And that sediment came from alluvium off the mountains. Now again, I'm not a geologist. I don't even play one on TV, so I'm not sure exactly which mountains came up first and stuff like that. But yeah, the source material is from the local mountains. All right. So now let's talk about Warren Subbasin. Next slide. All right, so here's Warren Subbasin. Okay, again, it's a pretty long, narrow subbasin. Now, if you look at the, I think the DWR definition, it kind of goes out. It's fairly large, but really the main alluvial material, groundwater bearing material, is in this long or narrow subbasin. All right, so you have the.
Oh, sorry.
So you have the Pinto Mountain Fault, and you have a number of other faults basically going north and south, and it tends to compartmentalize the subbasin. And I mean, we just called it hydrogeologic units, you know, west, midwest, mideast. You know, we didn't give a whole lot of thought about naming them, but each one of these is, I mean, there is hydraulic communication. They talk to each other, but not much because of this faulting. Let's see what else. Okay, so then, oh, no wonder I can't read it. So the primary recharge, again, is water coming off the Little San Bernardinos and the San Bernardino Mountains. It's coming in from, let's say, Water Canyon right in here. And it's less than, say, 200 acre-feet a year. It's not much. Okay. The primary discharge is water flowing out to the east out here across Yucca Barrier into Joshua Basin. Now, that's under natural conditions. So now, High Desert Water District has implemented an artificial recharge at their sites 3, 6, and 7. So now that's the primary source of recharge. And now, obviously, people live there, they've pumped water. That's now the primary source of discharge in the system. Next slide. So here's a cross-section looking west to east. There are 4 primary aquifers. Again, we didn't give a whole lot of thought. We have upper, middle, lower, and deep. Okay. You can see most of the wells are perforated in the upper, middle, and some are in the lower system. As you go from upper to deep, the permeability decreases. Okay.
There's that basement complex on the left that we're looking at.
Oh, sorry, yeah. And then this is that basement complex. Okay, again, this is looking east to west, right, or west to east. So this is the bedrock coming up here, and then you go out as you go west out of Yucca Valley. You start going up that hill. That's the basement's coming up right there. Now, someone asked about Morongo subbasin on the other side. That's not part of the Morongo groundwater basin. It may be called Morongo, but it's not part of the Morongo groundwater basin. They got that big mountain right there in the middle between them, so they're not hydrologically connected.
Those numbers are the different wells, is that, they just named that?
Okay, that's a shortened version of the state well ID number. Like 1 north, 6 east. I don't have my glass. Now you want me to put my glasses back on?
Are all wells listed? Like your website, would you list every well in this area? Every well? Because I think there's wells that you guys don't know about, right?
That's probably true. Yeah, that's probably true. Yeah, these are in our database. Granted. So yeah, there may be wells that we don't know about. Yes.
This includes both private wells and the wells that are by the water district?
I think there are some private wells in this list right here, yeah. But the ones that we know about in our database. All right, so this is just, again, this is, whoops, next slide. So these are contours of depth to basement or depth to bedrock. And here's where that divot is, that deep part in Warren subbasin is, where it's about 3,000 feet to bedrock. Okay. So, as I said, the survey's been working in this area since the 70s, early 70s. We started working most recently with Warren, or High Desert Water District, in the mid to late 90s, because they had some high nitrate concentrations in the groundwater. So in response, working in cooperation with High Desert, we installed 2 multi-level piezometer sites. Okay, so those are basically wells that we screened in particular depths, so we can get particular depth-dependent data. Okay, we collected water level and water quality data. We found that rising water levels in response to artificial recharge entrained downward-moving septic tank effluent.
What does that
mean? We're going to get to that. So we developed a groundwater flow and solute transport model, which has very little uncertainty. I'm just kidding about that. And then beyond that, we've looked at recharge studies at their site 3 and at the proposed wastewater treatment plant site. So this doesn't show the entire, okay, this is what's called a hydrograph. Okay, a hydrograph is basically time-varying water levels. So This doesn't show the entire record, but this gives you an idea. So basically, at this well, 36K2, which is, I believe, 9 East, their well 9 East, there was a 300-foot water level decline. All right, this is before they started artificial recharging. Okay, so that means that they're basically taking more water out of the bank than that was being put in. All right, then here in the mid-90s, they started doing artificial recharge at their sites 6 and 7, which is off Old Woman Springs Road. And then all of a sudden, all these dots are nitrate concentrations. You can see that the nitrate concentrations increased with the water levels and increased above what's called the MCL, the maximum contaminant level. And that's a rule set forth by a regulatory agency, the Environmental Protection Agency. So here we go, this is what we think happened. So in this cartoon, we think that there was septic tank effluent coming down, moving down through the unsaturated zone. Now, it's a constant flux, but it's not a whole, in the big picture, it really isn't that much water, so it takes time for that septic tank effluent to reach the water table. So it's going down, it hasn't really reached the water table yet. Boom, they put in the artificial recharge pond, boom, the water levels rise, and trapped or intercepted, or we call it entrained, the downward moving septic tank effluent, which has high nitrate concentrations. Now I was talking to someone else before this and explaining that we think it's septic tank effluent because we did water quality analyses and we saw that in the water samples there was like caffeine. Well, naturally occurring nitrate won't have caffeine in it, for example. So that's why we thought it was anthropogenic. All right, so here's okay, we've seen this cartoon before. This just shows the groundwater flow and transport model. See, we developed the groundwater flow and transport model to estimate not only what happens when you pump water and stuff like that to the groundwater levels, but what happens to the nitrate concentrations that are already in the water. So these are 500-foot by 500-foot grids. Remember, we have to pick discrete areas where we're going to solve for, in this case, nitrate concentrations and water levels. Okay, and if you look at my report, there are 4 aquifers, but because of, okay, we saw how much that thing was drawing down, right, 300 feet. It's actually dewatering the upper aquifer. And the model couldn't handle dewatering, so we had to make the upper and middle aquifer one model layer. That's a long story. I don't know why I just said that, but anyway, that's kind of an idea of the simplifying assumptions that you have to make. Sometimes it's because you don't know. Sometimes it's because the model may not be able to handle it, stuff like that. And these pink lines are the modeled faults that are in the system. So, what are the results? Okay. In the model, the total natural recharges are about 85 acre-feet a year. All right. Other previous reports said about 200 acre-feet a year.
An acre-foot's about a football field, 1 foot depth, 1 acre-foot.
Great. Yeah. Okay. That's a standard unit of measurement, but yeah, it's not much. I mean, you're pumping 1,000 acre-feet a year out of Warren Basin more. You know. Someone asked me, like, what's the error on this? Is it 83? Would I, go in front of, bet my life on it? Maybe not, but it's not 8,300. It's probably not even 830. Okay. The faults compartmentalize the groundwater subbasin. Okay, that is, they minimize how the groundwater talks across these, what we call the hydrogeologic units. Okay, the artificial recharge in the Midwest and Mideast, that's where sites 6 and 7 are located, basically stay in those units. And the flow across the Yucca Barrier into the Joshua Basin is roughly on the order of 85 acre-feet a year. So once we use this model, we can test water management scenarios like what if we built Site 3, what could happen in terms of water level response? What if we build a wastewater treatment plant and recharge X number of acre-feet, what's the water level response? And for an optimization model, what's the best way to manage your aquifer system, say to minimize the cost of operation or something like that? All right, so now, speaking of Site 3, okay, so we had that problem at Sites 6 and 7. They had high nitrates as a result of the artificial recharge. So High Desert wanted to be proactive. They were proactive. And so they said, okay, let's start looking at Site 3 before we start really artificially recharging. So USGS, in cooperation with High Desert, instituted a drilling and monitoring program. All right, so next slide. All right, so this is kind of an older picture, but here's Site 3 here with its three ponds. Okay, we installed an unsaturated zone monitoring site. Dave just talked about it. Right here between the three wells. We also installed our unsaturated zone monitoring site down here by the Elks Club. So we wanted to get an idea of what's going on in an urbanized area in terms of vertical distribution of nitrogen and nitrates in an urbanized area. And then we also installed a shallow one. It's not in the picture. In the space formerly known as the Blue Skies Golf Course. I don't know what it is anymore. I guess they're bringing it back? Oh, okay. Yeah, Dave was saying, look at the green, look at the green. Okay, so again, Dave touched on this already. We installed heat dissipation probes, advanced tensiometers, suction cup lysimeters, and a piezometer, which is a fancy word for a well at the water table. This is at both at sites 1, YVUZ 1 and 2. That is at the Site 3 site and at the Elks Club. Next slide. Okay, so again, you've seen this before. It was drilled with Odex. This gives you an idea of where we put the instrumentation. Here's the lithology. It doesn't really show up, but here at 200 feet, it's a change in source material from, I can't remember which one was which. One side, deep is the Little San Bernardinos and shallow was the San Bernardinos, or vice versa. I can't remember which one it was. But that was actually, turns out to be an important thing because, I mean, this is basically all gravity sand. You're looking good here. Even that change in source material affected the way that the recharge hit the water table.
What about the caliche?
We didn't find any caliche. All right, so here's pre-recharge soil nitrate concentrations. All right, so these things are in milligrams per kilogram, sorry. And then, okay, then here the lysimeters are milligrams per liter. All right, so basically nothing's happening at YVUZ1. There was no soil nitrate in the vertical column. Over here at YVUZ2, okay, in the Elks Club, we installed in the Elks Club parking lot, there's an apartment building right, I don't know, 20 feet away. There's the Elks Club, there's some houses to the north. Here's some lysimeters. You're talking almost 500 milligrams per liter, which is very high at about 150 feet below land surface. No, it's 100 feet, sorry, 100 feet. Then we have the other one at 150 at about 20 milligrams per liter. All right, so down here, this just shows the cumulative recharge at Site 3. Here's the time varying recharge, and here's the cumulative recharge down here. So here you see water levels in wells adjacent to Site 3. You can see water levels are, here, this line here is when recharge started at Site 3. Now, basically water levels are already recovering because pumping had decreased in the West Hydrogeologic Unit before recharge had started. But you can see here, man, once time recharge started, man, it really took off in terms of water level recovery. Okay, this well here, this black line here, is well 11W. At that time, they were pumping to supply half the water. Half the water coming out of the west was coming out of that well, so that's why it wasn't recovering. Plus, it was maybe a mile to the east of the recharge site. So based on water chemistry, the recharged water reached the water table very quickly. 42 days, 3 months, it's very quickly. Okay.
What's the source of that recharged water?
State Water Project.
That's what I thought. And that stopped, right?
Not as far as I know.
They're still doing it.
Yeah, they're still doing it. The high nitrate concentration observed at 90 and 150 feet below land surface. That is a concern, and that's why you should we should maintain monitoring for high nitrates in wells adjacent to Site 3. Okay, the last thing we're talking about, at least within Warren Basin, is the wastewater treatment plant recharge site suitability. So here we drilled on another unsaturated zone monitoring site. Okay, we did geophysical logs. We already heard about that. We cored it. We already heard about that. And collected water quality, chlorides, and nitrate data. We also did surface geophysics, and we did a small-scale recharge test. So a pilot-scale recharge test. So this is an old, next slide. Okay, I think Home Depot, this old picture here, but Home Depot's over here, right? Maybe Walmart's over here, all right? So, but this in general is where they want to put the wastewater treatment plant. And so this is where we put the unsaturated zone monitoring site. Next slide. Again, this is how it was constructed. There's the lithologic log. Next slide. Okay, here's the soil nitrate. Okay, we've got this high concentration of soil nitrate. Okay, so this is again milligrams per kilogram, I believe. Yes. So it's not exactly one-to-one. It's not one-to-one at all with milligrams per liter. And this is probably from natural nitrate. Okay, as plants degrade, decompose, they leave behind nitrate. They should be aware of it. All right, I think Dave showed this picture before too. Okay, basically here's the water. He did a pilot scale recharge test. He built a small pond around YV-UZ5. High desert, brought in a water supply. We maintained the pond elevation as shown by this green line. But basically this is how long it took for the water to get down to the ground, to the water table. What do you say, 135 days? So that's about an average movement of about 3 feet a day. That's pretty good. All right, so now Dave is going to touch on, discuss Joshua Tree and Copper Mountain. Can we wait till the end? And 29 Palms.
So moving, talk specifics, moving to the east, up Highway 62. Next slide. So we'll talk about the Joshua Basin. So USGS has worked with Joshua Basin Water District with the goal of improving understanding of the geohydrologic framework of the Joshua Tree Copper Mountain subbasins. So that's the goals or the objectives to determine the distribution and quantity of natural recharge, develop a groundwater flow model, because that's everything is to give Tracy work. Looking at both, so then also looking at artificial recharge and then land use effects on the basin. So here we have the Joshua Tree. So we were just talking about the Yucca or the Warren Basin here. Now we're in the Joshua Tree Basin, Copper Mountain Basin. They're divided by the Pinto Mountain Fault running east to west here. The Joshua Tree area is about 12.5 miles. Copper Mountain is about 13, and that's the water-bearing units of these areas. And then we'll move out and talk about 29 Palms next. Again, you're getting one. There we go. So natural recharge is coming in from the Little San Bernardino Mountains across the Yucca Barrier from the Warren Basin, about 84 acre-feet a year, and then some stuff even flowing out here from the San Bernardino Mountains. And just regionally, that's the water moves from these recharge areas generally from the west and south towards the east. So you typically get, the water is getting typically older, or it's been longer since it was a raindrop as you move this direction. That's a good kind of conceptual way to think of it as it's moving from basin to basin. Again, so natural recharge, just mentioned real quick, in those basins, less than about 200 acre-feet per year. So this is the Joshua Basin, so the town of Joshua Tree down in here, Copper Mountain Basin, Coyote, Playa Lake bed up here. I'm going to look at this cross-section in the next slide, BB prime. So we're looking along the axis of the valley. So you remember Tracy's slide, we have this deep sediment-filled basin. You can see the pre-tertiary basement or bedrock complex here. So this is the Yucca Valley or Warren Basin over here. We have the Yucca Barrier Barrier Institute for Mental Physics, or whatever the new name is located in here. So we're kind of moving down Highway 62. You can see the Joshua Basin divided into 3 aquifers, again creatively named upper, middle, lower. These here are the wells. I'm not going to say it's every well, but it's wells along this profile. You can see most wells, and then we have the water table here. Depending on where you are, up by the cemetery, it's very deep to water. It gets shallower down here, not because the water table is rising, but because the land surface elevation is decreasing. Most wells are screened in the upper, a little bit in the middle aquifers. And then you can see the deep aquifer is the thickest, but it's not very permeable and doesn't yield much water to wells, even though it's the thickest of the 3 aquifers. And then you can see we step across this fault over in 29 Palms we'll talk about next. So let's go to the next slide. So this is a contour map again of the depth to basement in the Joshua Tree and Copper Mountain basins. So you can see where would the community center be? It's hard to tell. We're probably out somewhere over in here, but down here you can see the deepest part of the basin, 4,500 feet to bedrock. Copper Mountain Basin's about 2,000 feet, and this is based on gravity surveys. So we haven't drilled wells down here. These are based on gravity data, which maybe we can talk about at the end if someone wants to. Next slide. So this is a larger story for all these basins in the desert. There's relatively little natural recharge compared to what is being pumped out of the ground, and that's because all these communities up here rely almost solely on groundwater as the source of supply. So it is a bank account. The bank account's being overdrafted. One of the manifestations of that is declines in water levels. So water's being removed from storage. So this is since the late 50s, with the advent of pumping, you can see there's been, at this well, 32C1, about 45 feet of decline in the Joshua Basin. That's the extreme example here. So the water, it is in an overdraft situation. Next slide. So USGS, in cooperation with Joshua Basin, first, when was this done? Early 2000s?
Yeah.
So developed what's called a geologic framework study approach. So you're looking, geohydrologic framework study approach. What does that mean? So it's comprised of data compilation and collection, which is looking at all water level, water quality, aquifer properties, pumpage, geophysical data, trying to understand the system. What data is available? Let's try to understand what's going on. Doing an estimation of groundwater recharge. There were 3 methods. So again, in this scientific method, we're trying to approach it from different angles, see if we get the same answer, see if things are in agreement with one another. And I'll talk about these in a second. And then as part of this, developing a groundwater flow model. So estimating that natural recharge, 3 methods, doing these field methods and borehole instrumentation. So we're doing field scale experiments to try to estimate how much natural recharge is going in the ground. Looking at temperature and matrix potential, the chloride mass balance, and this method came up with an estimate natural recharge less than 70 acre-feet per year. This is what's called a watershed model, looking at stream routing, soil vegetation, geology, and precipitation. This method came up with just under 160 feet per year, and then the groundwater flow model came up with about 125 feet per year. You know, these are all different answers. They're pretty close to one another. I know you'd say this is double this, but they're certainly on the scale of looking at what what you're pumping out. It certainly is a lot less, no matter how you look at it, the water that's going in. USGS then in ModFlow developed a groundwater flow model. So here's the Joshua Basin down here, Copper Mountain Basin here, Pinto Mountain Fault, and you can see it's modeled along these grid cells. So this is done to better understand the aquifer system, provides a tool for predicting future water levels, future nitrate concentrations given different management scenarios. So instead of doing the experiment, hopefully you can run the model and say, what if we try this? Where are we 50 years down the road? Can you go back one, Laurel? So the grid space in this, 820 feet by 820 feet, and again, that's the choice of how the model was discretized. Okay. So the results of that groundwater flow model, total natural recharge to the Joshua Basin based on that model, 207 acre-feet per year. And that's underflow, so coming across the Yucca Barrier to the west, 84 acre-feet per year. And then stream flow infiltration, mountain front infiltration, mainly off the Little San Bernardino Mountains at 123 acre-feet per year. The Pinto Mountain Fault compartmentalizes the two subbasins, so that's a barrier between the two. What we're saying here, 99% of pumpage from storage depletion, meaning 99% of the water that's pumped out of the ground is not coming from this recharge, it's coming from water that was sitting in there. So most of the water is coming out of the ground. And one way we think of that is that it's an overdraft. So the model could be used to test artificial recharge scenarios, and we're actually currently updating the model to more recent conditions. So Joshua Basin, being proactive, interested in artificial recharge, and including high nitrate problems that could be associated with artificial recharge, funded the installation of monitoring sites and further modeling. So looking at the feasibility of artificial recharge with this study, looking at effects of septage, entrainment of septage, as we discussed from the Warren Basin, and then some emerging contaminants. What that means, it could be pharmaceuticals, chromium, the MCL for chromium probably is going to be dropped by quite a bit in water quality, those kind of things. Next slide. So the objectives of the current study are to identify the vertical distribution of nitrate in the unsaturated zone, determining if there's a potential for denitrification, so breaking this down into innocuous nitrogen and oxygen components. Looking for a means to monitor the artificial recharge once it's happening using that unsaturated zone monitoring site. And then water management strategies to control nitrate concentrations, primarily in response to artificial recharge. Next slide. So here's how we're going about the study. So it's to characterize the hydraulic, chemical, and microbiologic properties of the unsaturated zone, looking at changes in water levels and monitoring water quality. So that involves primarily looking at water levels in wells, sampling from wells, and then looking at models to how to manage the water, looking at different scenarios, and then updating the existing model. Next slide. So we're running out of time. I'll go through these pretty quick. Joshua Tree, we have, of those unsaturated zone sites, we have 4 of them. 2 are adjacent to a residential area. 2 are out here near the artificial recharge plant. So one's looking at septage recharge. The other 2 of them are looking at septage recharge. The other 2 are looking at artificial recharge. They were drilled by the ODEX method, collect cores, drill cuttings, looking at hydraulic properties. We discussed the instrumentation that goes in those sites, and we did look at some microbiology, primarily as it relates to nitrate. So this shows the slides. So we're up somewhere down here at the community center. Here's the recharge facility. We have 2 unsaturated zone sites, and then the other 2 up here that are on Desert Air Road are looking at septage, and you can see the production wells. Next slide. This just shows one of the sites as an example. This is called JTUZ-1, Joshua Tree Unsaturated Zone 1. This is the first one we drilled. You can see the instrumentation, the lithology, generally very coarse, sand and gravels, that type of thing. This is the nitrate profile at JTUZ-1. So we intentionally installed this close to a relatively old septic system. So this is nitrates. This scale here is nitrate with depth over here. So you can see here at about between 80 and 100 feet, there's a large spike in nitrate. And this is probably from the nearby septage system. So the good news, the bad news is there's a lot of nitrate. The good news is it's a long way from the water table in this instance. But this would begin to be something you want to watch, not to, as the water levels rise, you wouldn't want to entrain that in recharge water.
And what depth is the water table at that site?
That site is about 520 feet. So it's, there's several hundred feet between. And that's a function of how much, there's not a lot of water coming out of these septic systems, so it's moving relatively slowly through time. It can also perch on different layers in the subsurface, that kind of thing. So next slide. So ongoing work with Joshua Basin, we're updating the groundwater flow model to look at solute transport and look at regional effects. And then there's ongoing data collection to establish pre-recharge baseline conditions, so before the water went in to the ground out here at the recharge site. So we're running short on time. I'm going to go through this pretty quick. So now we're going to move one step further to the east and talk about some work we've done out at 29 Palms. So here we have the Warren Basin, Joshua Tree, Copper Mountain, and then out near 29 Palms, the Marine Corps base out there. There's 29 Palms City, which is the 29 Palms sub-basin, And then the base out here is on the Mesquite, the Surprise, and the Dead Man Basin. And similar to these basins, you know, throughout the desert, most of the water is coming from storage, so there is an overdraft of water. As you move from, well, I'll get to that in a second. Can you go back one, Laurel, real quick? So we talked about, one more forward. We talked about spring flow. That's one of the things Tracy talked about. This Surprise Spring is an instance where you have this Surprise Spring fault right here. Water flows generally moving from west to east, and under pre-development conditions, the water hit this fault and backed up against it until it filled up what I would call this bathtub of Surprise Spring, and Surprise Spring subbasin. And right here, that's where that water was spilling over that fault. And so before there was groundwater pumping, you had that fault the water flowing at that fault at ground surface. Most of so in these basins, a lot of the outflow pre-development was underflow to the next subbasin. 29 Palms being the distal basin here, they do have these big dry playa lakes. Those are actually zones of discharge. So I don't know if you remember the slides Tracy showed where you have areas of recharge, and then we have to see those groundwater lines go, and then they discharge. Oftentimes where you see a dry lake, that's an area of discharge. So the water is actually evaporating there, and water is typically very shallow in those lakes. So a lot of the discharge, the natural discharge from these subbasins is actually at these dry lake beds. That's the natural process where the water is leaving them. And there is some underflow to neighboring basins. So the basins here, we're talking about what's called Giant Rock, Surprise Spring, and Dead Man. These subbasins are divided into 3 aquifers, again creatively named upper, middle, lower. You can see the water levels here. Quite a few of the basins, the water levels down in this middle aquifer. This is from east to west across the base. You can see it's very subdivided by faults. West-east, excuse me, across the base. And then you can see how each of these faults, this is really illustrative, act as barriers to groundwater flow. And oftentimes out here in the desert, you may not stand here on the land surface and say, aha, there's a fault here. But if you have a well over here and a well over here and the water levels are appreciably different, you can start to think, okay, maybe there's a fault somewhere in between here. How can we look at other things to see if there is a fault here? And that's a colleague of mine, John Isbicki. He always says, because you get excited, you see different water levels. Oh, we found a fault, let's name it. And he says, just be careful. Every time you don't understand something, don't go drawing in a fault, because you can get in trouble. You may just not understand what's going on. It doesn't necessarily mean that there's a fault there. You can see here, so yeah, Dead Man Lake, even under current conditions, the water table's very close to the old playa lake surface. So that's where you have your discharge. You can get evapotranspiration out of the lake. That's the natural discharge from the basin. Next slide. So again, wells, we have declining water levels from the 50s to today, just like every subbasin out there. There is the pumpage exceeds the natural recharge, which is going on throughout all the subbasins for the most part that have been developed. So we did develop, just like everywhere else, a groundwater model for the 29 Palms base. The major salient points that what the model determined, as I said, most pumpage comes from storage. Did some water management issues. So you can see these are the grid spacing up here. The green lines are the discretized faults. And so this is one method of looking at scenarios, and one of the things out there was there's declining water levels in Surprise Spring Basin. If you can reduce pumpage in that basin, you may reverse the water level declines. And the model helps to quantify some of those scenarios down the road. Instead of enacting and saying, oh, we'll implement this policy for 20 years, you can run the model for 20 years. I don't know how long it takes, 20 days,
I don't know.
however long, to then look at those scenarios.
What's pumping out in that sub-basin, though? There's nothing out there.
There's the Marine Corps base.
Yeah, but I thought they were further over. Okay.
No.
I believe the way I looked at the map, that was off in the boonies.
That's where they're at.
Well, yeah, but I know, but.
So let's go one more slide, Laurel. I think we're... Okay, I'm going to... The last thing I want to mention, so we kind of moved through the basins up here that the USGS has done studies in, and that's not to say there's nothing interesting to say up, say north here up 247. We just haven't done as much work, so we don't have all the pretty pictures to show that kind
How
of thing.
about Pioneer Town? I understand that their water table up there has a lot of arsenic in it.
That's possible. So arsenic can be not to digress too much, arsenic can be naturally occurring. Oftentimes you find it in association with granitic rocks, and I don't know much about Pioneer Town, so this is somewhat speculation, but it may be related to the geology if there are high arsenic concentrations. I wanted to mention, so the USGS since 1992, in cooperation with the Mojave Water Agency, has constructed a series of regional water table maps. We do these about every 2 years. It's hard to see here. This is the let's see, the Mojave Water Agency management area is this red line. The purple here are the Morongo basins. So we deploy numerous scientists every 2 years to collect water levels, to try to get a snapshot of what's going on in the Mojave area. And so this is publicly available. It's updated again every 2 years. So this is kind of a regional idea, looking at how water levels are affected throughout the area, which does include down here. So this is really a big scale picture of what's going on. And like I said, so this is an online interactive map. You can pull up all kinds of different layers. You can zoom in and look at your basins here, so you can see water level contours through time. And that's, we're a public agency. It's all publicly available data. 4 minutes.
All right, so on the flyer for today's meeting, there are some 4 primary questions, I guess, that were burning questions. So that were being posed by folks in the area. So first is the Morongo Basin has how many different aquifers? All right, Ray talked about that. There's many different sub-basins. I didn't even count them, but there's quite a few. Each sub-basin has a varying number of aquifers. Okay, the Warren has 4, Joshua Tree and Copper Mountain have 3, and 29 Palms Marine Corps Base has 3. So it just depends on the location. All right. If not an underground lake, then what is an aquifer? All right, we already did that. We're not going to answer that again. No, it's water stored in the pore spaces within the alluvium, right? So there's dirt and there's water mixed together. Water's in the pore spaces between the granules. All right, what makes the water so different from neighboring aquifers? Well, in general, they really aren't that different. It's primarily water quality. We didn't really touch on geochemistry, and we would be happy to come back and have a geochemistry 101 meeting. We probably won't have as many people show up. Not after today. Anyway, but it's water type. So Warren Basin has a calcium sodium bicarbonate type water. Joshua Tree has a sodium bicarbonate water, and Copper Mountain is variable from well to well. We don't know exactly what's going on with that. And a lot of it's depth geology or geologic dependent. So as you go deeper, the water quality usually gets poorer, and shallower, the water quality is better. And then this calcium, sodium bicarbonate business are our natural constituents, major ions within the water. And then obviously there's an anthropogenic effects. So from basin to basin, right? So in Warren Basin, you're artificially recharging water with state water, so you're changing the water type. In Joshua Basin, you haven't started that yet, but you will pretty soon. And then obviously there's septic tank effluent and things like that. What can hurt and protect our groundwater? Well, anthropogenic pollution, septic tank effluent, gas stations, various spills, overdraft can affect your groundwater system. What can we do to protect your groundwater system? Well, you can protect your recharge areas. Right? If you want to have any kind of recharge in your system, you got to protect your recharge areas. Well, here I think you're pretty good because a lot of it's at the national park in this little San Bernardinos. Wise water management. I don't know, I mean, we're in a desert, I don't think I have to say some of this stuff. Okay, limit or eliminate pollution sources. I mean, again, that's kind of, this is kind of common sense listing type thing here. Okay, so before we close on for questions and stuff, and I think, Laurel, you made this list available?
Yeah, the list is available over there.
Okay, so there's this list of publications is available on the table over there. Help yourself as you leave. But here's the various reports that we've published that deals with this local area. So we'll open the floor to questions. You were very patient.
What are the real life effects of having higher nitrate levels?
Well, what are the real life effects of high nitrate levels? Well, high nitrates can result in what's called blue baby syndrome, which obviously, I can't remember exactly what the biochemical thing is. I think it replaces oxygen in the bloodstream. So the kids get actually blue from lack of oxygen. But I'm not okay. So, but it's in a higher concentration. I don't know what it does to adults, to be honest.
I don't know what the toxicity level. That's the big issue.
Yeah, I don't know what the toxicity level is, but the MCL is 45 as nitrate. 10 as nitrogen. Milligrams per liter. Yes, ma'am.
I noticed in the maps, the barriers between 3 lines. What does that represent?
So she's asking why the 3 lines representing the Yucca barrier. We think there are 3 unmapped faults that make up the Yucca barrier.
And if there were no people living here at all, what would that mean to depth to water over time?
It would be unchanging. It'd be what you call a steady state condition. So inflows and outflows would equal each other, and you'd come to some kind of equilibrium. Yes, sir. In the back.
You, when you're talking about the rock history basin of the rock first, you're talking about an upper layer, a middle layer, and a lower layer. So I assume you know the volumes of or rough approximation of the volumes of each one of those layers, correct?
Not off the top of my head. We could calculate
No,
it.
I'm not asking that, but
Yeah.
that's something the USGS would have calculated, right?
It is. We did not calculate it. It's not in our reports, for example.
Right, but so when you come up with these numbers for reserve levels, they typically talk about the aquifers at the current level being used, having 100 or 200 years of reserve. Are you talking in those calculations, does that include the deeper layers of the aquifer as well?
I don't believe we've ever said that.
Well, these are the numbers you hear tossed about quite often.
Okay, but no, USGS, it's not our policy to report those kind of things. How about someone new? Anyone new? Oh, you were new.
What's the impact, if any, on recharge rates with, say, non-native plants, pine trees and that kind of stuff? Is that at all an impact?
I mean,
Oh, what's the effect of non-native plants on recharge?
well, if you're using more of your groundwater to water a non-native plant, then yeah, it's gonna.
Just say you're not. I mean, some of them seem to be surviving out here without.
Yeah, we're not botanists, but we don't know how well they compete compared to native plants. But yeah, I don't know. You in the back.
Yeah, I was just wondering, when you talked about protecting a recharge and you were talking about the mountains, would it make sense that whatever your recharge pond is, like you said, next to the urban area, once it gets to a certain level, it can grab those nitrates that are in the septic? So when you think about where you put a recharge pond, would it make sense to put it at a low spot that was, not going to go through those urban areas? And the other thing is, could you actually recharge the water below the ground and bypass that septic?
All right, so there are a couple questions there. One was, could we bypass the septage that's in the unsaturated zone? And something about placing the recharge sites. I'm sorry, I didn't.
In the best spot possible to avoid that septic.
Well, that's a hard one to call. I mean, there are various economic questions to answer when you're placing a recharge site. Not only is it where the land available, but then you got to put in wells, you got to pipe the water back to wherever. So that's why, well, again, Joshua Basin was very proactive when they said, okay, we want to build this recharge site. What's the best thing we do? And we said, well, we should put an instrumentation in there. So we put in that unsaturated zone monitoring site right in the middle of the ponds, well, what will be the ponds, so we can watch the water go down, we can watch the change in water quality, and we can basically watch what's going on. Also, we would also strongly recommend that maintain monitoring of the water quality and water levels, because we know that if water levels get too high, then maybe you want to start being more concerned because you're approaching those high nitrate levels, high nitrate zones. Could you bypass? Yes, it's called ASR. What's it?
Aquifer storage and recovery.
Thank you, aquifer storage and recovery. But that's injecting water. Okay, so you basically, instead of pumping the water out, you're injecting the water in, but that costs money because then you got to pay for the electricity to jam that water into the ground. So, but yes, you could. Orange.
You've talked about us overdrafting our aquifers and that Joshua Tree is being proactive in putting in a recharge basin. Does the USGS develop any data around without recharge, how long the aquifers would last?
No, I think that question was asked. No, we don't do that. But it could be, well, some of it is, kind of personal preference, for lack of a better word. I mean, you can calculate it. You can go onto the maps that are in our publications and roughly estimate the area and say, okay, well, if it's, what porosity is, right? So now you can calculate how much water is in storage. Okay, you can calculate that off just the back of the napkin calculation. And you can do it for every aquifer. But, there's certain things that you got to remember. One, you're never going to get every drop of water out. Okay, some water is going to be bound to the porous medium, and you're never going to get it out. Two, once you start pumping it from deeper and deeper and deeper, it costs more to pump it out. The water quality decreases as you go deeper. So then, hey, now what are you going to do? So, it's like one of these things. We just, the USGS is in the business, for lack of a better word, of basic science and science data collection, data interpretation. And we provide those data to the decision makers, in this case, Joshua Basin Water District, and they, and with your input, make your decisions. But we don't, like, for example, in our reports that are shown here on this list, we don't calculate how much water is in storage, for example. I'm sorry, besides you two, one of you two.
Are you still using the ground flow model that was developed, I believe, in 2003?
Which, for Warren Basin?
Yes.
We're using it. Well, yeah, we did. Yeah, we are. We are using it. We developed actually an optimization model was recently published using that model.
So you're using a modified version of that model?
We updated it to maybe 2010 conditions at the time, and then we implemented what's called an optimization, which looked at optimal location of pumping and recharge wells out actually at the wastewater treatment plant, and it's published in Groundwater, I believe. Purple.
Regarding water policy, I know you said it, but are there other people doing research that water policy makers use that research, or are they using only USGS research?
Well, I hope they only use USGS research. It's only right. No, yeah. I mean, the USGS is not the only people that are doing basic hydrologic research. Academics are doing basic hydrologic research. I think the National Park Service does basic hydrologic research. Private consultants. It's a little bit different, but yeah. I mean, no, we're not in the. We don't have the market cornered by any means. Hat.
Is County Lake an area of recharge or discharge like Tri Spring?
Well, yeah, but then the water table is pretty far below Coyote Lake. So it's not like in contact or really shallow, where the groundwater is really shallow at, is it Dead Man? Dead Man. So it's a little bit different hydrologically, but it is, in general, would be a discharge location.
It's still a discharge.
It would, still. You know, I don't know exactly what the water levels are out there, but I bet you in steady state and in pre-development it was a discharge area. Whether it still is, I'm not sure. Black guy, right there. Yeah, you're wearing black, yes.
I know you guys are really terrible at giving opinions, but does the basic science tell us that our local water agencies are being proactive enough about conservation? Because I hear a lot about overdrafting and drafting out of water tables much faster than it's recharging naturally. Do you think they're reacting enough to the information being provided, or do you feel like your science is just being left in the dark, or they're acting too slow? I have a really hard time believing the water districts because they're reliant on a business model and they don't have a lot of business.
Yeah, look at the time. Oh, we got to go. And if you think we're going to answer that question, you're. I mean, you know, we talk to the water agencies. They don't ignore us. I don't know what else to say. We talk to them, and it's a good working relationship. I'm not going to go beyond that. I don't think I have no idea, really. Yes.
Yeah. You said, I think, that we get the geometry basin, that 200 acre-feet a year natural recharge, 84 acre-feet comes across Yucca Barrier, but that's almost half. Is there any implications for the location of that sewage treatment in terms of bad stuff coming over Yucca Barrier?
Well, you know, I don't know what what level of treatment they're going to do in Yucca Valley. Yeah, it's going to be more than septic. It's going to be probably tertiary. It's going to be pretty clean. My guess is going to be pretty clean. Will the flux across Yucca Barrier increase? We did a model. We used the model. Someone was asking, do I actually use the model? Yeah, we actually use the model. I can't remember what it increases, maybe double to maybe 160 acre feet. I don't remember exactly, but over time the flux rate will increase across the Yucca Barrier, because I mean you're raising water levels in that east area, and there's not much pumping going on there. Yes.
Is USGS currently doing any studies in the state of California evaluating the impact of fracking on groundwater?
We're just starting to talk to the state of, okay, he's asked about, is the USGS doing work about in fracking in California? I think we are. I mean, we're talking to DWR right now, but is there a program in place? No, there is not.
So the water bill, you guys have.
Well, we're talking. They got it. Someone's got to fund us.
No, I know.
Yes, lady in the back.
I see that the Mojave Water Agency is hosting a talk in May by a permaculture designer on water recharge and keeping water on your land and permaculture techniques for recharging aquifers. Has the USGS started to look at this at all?
So you're talking about like a local scale, like private level?
Well, private scale or county scale. I mean, it can scale up. It can go to any scale. So.
Well, I'm not. I mean, not that I'm aware of.
Well, you should.
Again, what we do is we talk to the water districts, water agencies, and say, hey, what's up? And they say, hey, we're thinking about doing our artificial recharge thing. Hey, we do this, that, we drill wells, we can model it, we can do this, we can really help you out. And they say, great, let's work together. But so I'm saying that there's got to be interest on both sides.
Oh, we're interested. We're seriously interested. Can I get your card?
Sure. Yes, sir. Back standing. Oh, too late.
Well, this is a personal question of you, actually. You were drinking some Coca-Cola rather than water in the water district, talk. Does that mean that the water is not good enough to drink around?
It's conservation. I need the buzz. That's what it means. Yes, ma'am.
My question is on the recharge water that we're getting from Northern California. Is that tested for nitrates before it comes to us?
Yeah, there is and I don't know the full suite of analyses. The State Water Project does track it, and then our plan to monitor the recharge. So with that monitoring site, as part of that study, we'll actually sample the water as it goes in. Not only looking at nitrates, you want to look at the constituents like dissolved organic carbon, and then we look at things that are called stable isotopes of oxygen and deuterium, which are actually, so that's hydrogen and oxygen. They're part of the water molecule. That is one way to try to understand, it's a fingerprint of the recharge water and try to compare that to native water. So that will be monitored. And that's a good question. I think the state, or the water project does do monitoring at various points along, and I'm not sure if nitrate's a part of that or not.
Yes, ma'am.
Are you doing any studies that would help us to understand how to enhance natural recharge, how to get the water that comes through Quail Springs into a place where it is useful and build our aquifer?
I mean, what would come down those washes is pretty useful. You know, it's typically, so throughout the Mojave, the places that the water gets in most efficiently are beneath the washes, because it's been wetter. That's where water's flowed in the past. Someone mentioned caliche. Caliche layers under those washes have typically been dissolved because it's been washing down for thousands, if not tens of thousands of years. I don't know if that answers your question.
But we aren't doing any studies per se on recharge runoff capture.
We did not capture. We did a study, and it's in one of the reports. They were looking at what is on Quail Wash when a storm comes through, trying to quantify the amount of water that was then percolating in.
Yeah, that would be the Joshua Tree and Copper Mountain Subbasin Model report.
So that's part of that report.
Do you remember now?
I remember my question.
Okay.
I know you've been collecting data for a long time on a lot of different aquifers, but have you ever seen a case where you collected data and then a major earthquake had happened and that caused the volume of the aquifer to change drastically?
Yes. Yeah, you can look at hydrographs at what was it, the Landers, I think. Hector Mine, and we have hydrographs from that. I forget what the water level change is, but in the well, through time, right on the earthquake, the water level went up like 20 feet and then dropped another 20 and stayed down. So it actually changed the geometry of the aquifer enough to alter water levels, and you can see that. And that's one thing I kind of do. We've got all these sites, and I actually get emails. Anytime there's an over a magnitude 2 earthquake in the Mojave Desert, I get an email, and I'm comparing those to water levels to see if I can see them. The tough thing is a lot of our monitoring wells are in the shallow systems and the unconfined aquifers. That's what we're monitoring most closely. The responses you typically see are in the deeper confined systems, and that has to do with aquifer hydraulics. You typically see more of a response in those confined systems to earthquakes. But yes, that is documented, changes in water levels.
But we don't calculate the...
Sorry?
Have you ever seen one totally destroyed by earthquakes?
A well?
You could no longer use it?
No,
aquifer. Oh, the aquifer? I have not seen that,
no.
But...
Yes, ma'am.
Hey, I just wanted to thank you. I know you guys have to get head out, and I wanted to thank you on behalf of Joshua Basin for coming on here today and putting this on.
Our pleasure, our pleasure.